Hello everyone, welcome to the 15.1 video, the start of chapter 15, the start of integration of multivariable functions. And this is, I think looking back on it, people feel like this is the major topic of Calc 3, and they're probably right. Partial derivatives maybe seemed to go by quick and easy, and all the other stuff maybe you don't even remember anymore from the beginning of the course, but this integration of multivariable functions, it's gonna make an impression on you, I'm sure. So you'll think back on these days fondly. So let's go ahead and start developing the theory. So just as in Calculus 1 and 2, how did those courses proceed? We started with the idea of limits and continuity, and then we worked our way up to derivatives and finally to integrals at the end of Calc 1, beginning of Calc 2. And we're kind of at that stage for the multivariable stuff. It's gone kind of fast, right? So we started with limits and continuity, and then we did partial derivatives, and that ended in the last chapter. Now we're talking about integrals. Okay, so remember the intuitive, kind of naive way to think about an integral. Not that naive is bad, it's just you know, we have this idea of the definite integral from Calc 1 as maybe the area beneath the curve, but that's a really limited definition, right? It's good in that it kind of gives us a geometric intuition to what's going on, but that's not the whole story of the integral, right? The integral is more than just area beneath the curve. Okay, so if this curve is my f of x, and I have this bounded interval a to b, okay, I can talk about the area beneath the curve, right? This shaded region. And as you hopefully recall, that value there, this value of the integral, or excuse me, this value of area is what we're going to find with our integral. Okay, so our integral f of x dx from a to b, let's kind of stick to definite integrals for now. That is, we kind of think of that as the area beneath the curve. All right. And then what would we expect for a multivariable function? And in this section, we're going to stick to functions of two variables, but this stuff is true. The integral we're going to develop works for higher dimensions. It's just that we would have to expand our little bit of thinking, but the exact same process can be used for higher dimensions. But let's stick to 2 dimensions for now. So if in a single variable our integral gives us the area beneath a curve, what would you expect from the integral for like R2 to R? Okay. So let's say this blue surface, is my the graph of my function. What do you think the integral? Okay, we haven't really defined the integral, but if I construct some integral of fx y, okay, d something, what do you expect that integral to give us? Maybe intuitively, instead of area beneath a curve, we can think about it as the volume beneath that surface, right? So we see this surface, if we kind of drop it down to the xy plane, it kind of gives us a 3D object, right? It's almost like a box, but then the lid of the box is my curve. So it's kind of an irregular box shape. So I could think about the volume of that weird box. You know, I could think about the volume of this shaded region, and maybe my shaded region, instead of just a 2D shaded region, maybe it's kind of like all this stuff in my 3-dimensional space. So that's kind of what I expect from the integral of my multivariable function, the volume underneath a surface. But again, just like the area beneath a curve is kind of a naive way to think about the integral of a single variable, that volume beneath a surface is, you know, it's a good starting point, but we don't want to confine ourselves to that too much. So let's remember how we formed the integral in our single variable calculus course. Okay, we kind of started from this viewpoint of wanting to find the area. Okay, that's fine for a starting point. How did we do that? How did we approximate, you know, we start with an approximation to this area. And how did we do that? We started with rectangles. Okay, so I chop my, let's do this in a different color. How about yellow? I chop my area up into these rectangles. Like this. And rectangles, the areas of rectangles are easy to find, right? That's what's good about using these rectangles for our approximation. And if I add up all the areas of these rectangles, that's pretty close to the area underneath my curve, right? So what is the area of, let's say, what is the area of this rectangle in particular? Well, we've chopped our x-axis up into kind of increments. Okay, starting at a. So let's call our a equal to x0, and then this is x1 and x2 and x3, blah blah blah, all the way to xn. Okay, so for any random rectangle, what is the width of this rectangle? Let's say this is at some general xi, and then this would be xi plus 1. The width of that rectangle, which we can call delta x, is xi plus 1 minus xi. And let's just assume for simplicity, all these rectangles are the same width. Okay, so the width of this rectangle is delta x, which is xi plus 1 minus xi. And then what is the height of this rectangle? Well, it goes up until it's kind of close to my curve. So I could pick really any point on my curve in this interval, and that would be a pretty good approximation to the height. Okay. So let's say f of xi star, where x of I star is in my ith rectangle, is not in the rectangle, but is the height of my ith rectangle. Okay. So xi star is somewhere in between these two, and then I plug it into my function, and I get a point up here, and I call that my height of my rectangle. Okay. So f of xi star times delta x gives me the area of one rectangle, and then I add up all those areas, and I get all the areas. I get the total area of all my rectangles. Okay, and what does that sum of a rectangle of areas of rectangles look like? We use this notation here, this sigma notation. Okay, so remember, this just means I'm adding up n objects. Okay, I use just a little bit of different indexing than the book, but don't worry about that if you've already spotted that difference. They're completely equivalent. Okay, so we call this thing, remember we call this thing a Riemann sum. And then what we do is we take the limit of this delta x to be smaller and smaller. Okay, this delta x is the space between rectangles, right? So if I make this space between this width of rectangles smaller and smaller and smaller, my picture is going to get more and more accurate, right? Like if I kind of made these rectangles even thinner, what happens? If I made these rectangles super thin, okay, there's one, there's one, there's one, there's one, there's one, there's one. You see it's a much snugger fit to my curve, right? So my approximation to my area would be better. Okay, that's the intuitive idea. So if we take the limit as that delta x, that width of the rectangles gets smaller and smaller and smaller, we should end up with our actual area. And this limiting procedure is how we arrive at our integral. Okay, so we take the limit of this Riemann sum as delta x goes to 0. Okay. And what happens? So we take the limit of this thing and it becomes our integral, right? So this summation sign becomes an integral sign. Instead of having fxi where xi is some random point in a small interval, we just end up with f of x. We're considering all our f of x's. And then instead of getting this kind of chunk, this kind of interval that's the base of a rectangle, I just end up with this dx term, which I can think of as kind of, this is the width of a rectangle up here, right? I can sort of think of this very informally as the width of a single point. It's basically a rectangle that's so thin, it's like a single point. It's only a single point thick. And that's, you know, that's kind of a sloppy way to think about it, but it's you know, as far as intuition goes, it's not too bad. Really what this is a measure, denoting a measure, but that's a topic for another time. So we have a similar process for multivariable functions. And we're going to focus on the case for function f from R2 to R. But as I said, it's going to hold in general. Okay. So again, this was just a recap of how we constructed our integral for Calc 1. Okay. So let's begin our construction for integral in our multivariable case. And we're going to start by developing a Riemann sum. Okay, so let's kind of again confine ourselves to this idea of trying to find the volume beneath the surface. Okay. And let's say I wanted to first, I can't find my, maybe I don't have the techniques yet to find my volume exactly, but I could approximate my volume in the same way I approximated my area in my single variable case. Now, to make things a little bit simpler, let's just assume that the function we're working with is defined on a rectangle, a nice rectangle. So that's kind of what I've drawn here, right? It's, you know, it's kind of a sloppy rectangle, but this domain here in the XY plane, it's a rectangle. Okay. So let's stick with this case where this domain is a nice rectangle. Okay, that's going to make our lives a lot easier. Good place to start. Okay, and let's call that rectangle that we're working in, let's call it D. The book uses R, capital R, but I'm using my own notation a little bit here. Now, how would we approximate the volume of that blue surface up there? Well, we could do with, let's see, we could do that with, instead of rectangles, like flat rectangles, we could just approximate our volume with rectangular boxes, okay? So going back up here to this picture, okay, if I wanted to approximate this volume, let's see if I can draw some rectangular boxes that make some sense. Okay, and I don't even really need my axes. Okay, let's say I'm working on this region and I want to approximate that volume there. How could I approximate this? Well, let's use yellow again. Let's say I start by kind of making a square here, and then making in my domain, and then make a rectangle, kind of a rectangular box out of it. Okay, so what would that box look like? It's going to be hard to draw these, but okay, boom. Okay, it would be in the corner here, and I'd have this kind of box. And it has a flat top, right? So if this blue surface has some contour to it, you know, there's going to be maybe a little gap in here between the lid of my box and my surface. Okay, but it is, you know, if it's a kind of well-behaved function, you know, nice, continuous and all that, you know, my rectangular box is going to be a decent approximation, right? Okay. And then I do another rectangle right next to it. Boom. That also goes up to my surface. Okay. And then I do another one next to that. And maybe this one goes up a little higher because my surface goes up higher there. And so on and so forth. And then I do rectangles coming this way as well. All right, I do rectangles here. Now it's going to start to get messy. But you see what the process is. I fill in all of this surface with these rectangles. Okay. So let me just erase all that now so I can copy and paste this thing again. Whee! Okay. So we're approximating our volume with these boxes. All right. Now to use this approximation, we need to be able to calculate the volume of those boxes, right? So okay, let's say our boxes have square, well, not square bases, but at least rectangular bases, and then then the volumes of these boxes would be the area of the base times the height. Okay, so let's kind of state that real quick. Base the box. I apologize if you keep seeing those assignments pop up from people. The bases of my boxes are rectangles. Okay, and then we have a height to our boxes as well. So the volume of our boxes, of our individual boxes for my approximation, equals what? The area of the base times the height. Okay, so I'm making these boxes to approximate my volume. I need to be able to figure out what the area of the base is and what the height of the box is. Okay, so let's start with the bases of the boxes. Okay, so let's say this is the domain of my function that I was looking at before, or, you know, any function with a rectangular domain. Okay, so let's say this is our domain, and let's see, and let's call it D again. Okay, capital D. So remember, this is our x-axis and this is our y-axis. So let's say our rectangular domain goes from A to B on the x-axis. And on the y-axis, it goes from C to D. Okay, I'm going to divide, let's look at just this x-axis here. And, you know, we don't even have to think about that rectangular domain. Just think about this x-axis here between A and B. I'm going to chop that up into m pieces. And let's just assume they're all of same width. Okay, so I'm going to chop this up into a bunch of pieces. Okay, and maybe I'll call this we'll say that's XO, and then X1 and X2 and so on, and I get all the way to B, which actually it would be n plus 1 pieces, but we'll call this B, no, XM. Okay, I guess now this is just m pieces. All right, so we chop our x-axis up into these m pieces, and then I do a similar thing for my x-axis between C and D. I chop this up into n pieces. Okay, and I'll call my C my point XO, or let's see, not XO, YO, and then Y1, Y2, so on, all the way up until D equals YN. Okay, and all of these pieces are the same width. Now, let's say the width, the width of the two axes, the chunks of my two axes are not the same. So maybe these all have one width along my x-axis, and these all have another. Okay. Now, what does that do for us? We're looking for rectangles, right? Well, think about a grid. Think about forming a grid from all these like hatch marks. Okay, so like from this hatch mark here, we would have a line, a straight line that goes like this. And then from this first hatch mark on the y-axis, we have a line going like that. And then I have all these lines, right? And I can see this is chopping my domain up into rectangles. And all of these rectangles are going to have the same area, okay? Like all of them have the same kind of lengths of sides, like this side is equal to this side is equal to that side, and then these sides along the y-axis are all the same, okay? So this is chopping my domain up into rectangles, and these are going to be the bases of my my boxes I'm using to approximate volume. Okay, so we've divided our interval AB up into n pieces, and we've divided our interval CD up into n pieces. And so this gives us a bunch of rectangles. How many rectangles are there? Well, m times n, right? There's going to be a total of m times n rectangles, okay? Okay, so let's pick a random rectangle and call it, we could make this very orderly, and we could talk about, like, we could kind of give each rectangle an address, if you want to call it that, or an index. So let's pick a particular rectangle and call it rectangle Ri sub ij, meaning, okay, it's like the ith rectangle along the x-axis, or the ith hatch mark along the x-axis, and then the jth along the y-axis. Okay, that's not too important. But we're just picking a particular rectangle. And what is the area of this rectangle? Well, let's see. Well, the kind of coordinates of this rectangle, it would start at x value xi and go to xi plus 1, and then its y values would start at yj and go to yj plus 1. Okay, so it would kind of look like this. Okay. Now, what is the length of the x side? Remember, we're saying all those divisions along the x-axis have the same width. Let's just call it delta x. You don't have to be too specific. And then what's the width of this side? Well, we'll call that delta y. All right. So what is the area of this rectangle? Well, it's just delta x times delta y. Okay. And let's go ahead and denote that area as delta A. Okay. So that area, delta A, is equal to delta x times delta y. Okay. And as we said already, each of these rectangles is going to form the base of one of our boxes. Now, what is the height? We can talk about the height now, the height of these boxes. Okay, so let's stick with this rectangle IJ. What is the height of that particular box with the base of the base is that rectangle? Well, it doesn't really matter. It's just we're going to pick any point in our box. So kind of going back up to this curve here. Let's see if I can do this neatly. Let's say I'm approximating this volume with rectangles, and let's look at a particular rectangle. Let's kind of look at this yellow rectangle here in the center, and let's draw the kind of corresponding box for that rectangle. Okay, so maybe it's got this box here that kind of goes all the way up until I hit my curve or get close to it anyway. How tall should my box be? Well, I'm just going to make it as tall as my function at some point. So let's pick like a particular point. What color haven't I used yet? Let's pick this kind of green dot inside my rectangle, and then I'm going to make the height of my rectangle f, the function of that green dot. So I plug that green dot into my function, and maybe I get this green dot up here, which is exactly on my blue surface. Well, I'm just going to make my rectangle, my box that tall. Okay, and that's the process I'm going to use for all my boxes. I'm just going to pick a single point inside my box, plug it into my function to get a point up on my surface, and I want to call that the height of my box. Okay, and that's a pretty good approximation to like all the height of all these points, right? If my function is, you know, fairly smooth and doesn't change elevation too sharply, all of these points, like on the blue surface here, they're all going to be close to that height of my green dot right there. Okay, so that's a pretty good way to choose the height of my boxes that I'm using to approximate my volume. Okay. Where were we? Okay, so that's how I'm choosing my height. All right, and now I have the area of the base of my boxes, and I have the height of my boxes. So now I can talk about the volume of these boxes. And again, I'm just restating what I said here, that if f is well behaved, if it's like continuous, that height is not going to, the point we choose inside our box is not really going to matter too much. And just for the sake of notation, I'm calling that random point we choose, I'm calling it xij star yij star. Okay, and then like I said, I'm plugging in my function to get a height. Okay. And as I said, if f is continuous, all those points are going to be, all the points near this should have about the same height. Okay, so that's a good approximation to our height. So now we have the height of our boxes, and we have the area of the base. So now we can talk about the volume of each of those individual boxes. What is the volume? Okay, I've got my sample point. I've plugged it into my function to get a height. Okay, so this is exactly the height of my box. And then what's the area? It's this delta A, area of the base. So if I multiply these two numbers together, I get the volume of that box, right? So that's the volume of one box, and I want to add all the volumes of my boxes together. So what would that look like? Okay, it would look like this, and it's not just a sum, it's a double sum. Okay, why is that? Going back up here to my picture. Okay. What rectangles am I adding up? Kind of going back to the corner here. I start by drawing maybe a rectangle or a box in this corner that goes up here, okay. All right, and then I got another one next to it. So to get the total volume, okay, what would I need to do? I would need to add up all the boxes going this way. All right, so but that just gives me one row, okay, so I could think of that as like, that would be what, from, we're calling those our i's, I equals 0 to m fx I j star y I j star, okay, delta a. Okay, so that would give me one row of boxes, but I want all my rows, so I add up all these boxes in my row, and then I need to add up all these rows. Okay, so I need another sum notation here from j equals 0 to n. Okay, and then that'll add up all my rows. Okay, so that I see why I need this double notation, double summation now. Okay. Sorry, a lot of scrolling in this video. Okay, so we get this. So this is our approximation to the volume underneath our surface. Now, just like with the single variable case, we expect, and for our nice continuous functions, this is true, that if we make the size of our bases smaller and smaller and smaller, the rectangles are going to get well, the approximation is going to become more and more accurate. Okay, just like how in the single variable case, you know, we chopped our interval a b, we chopped it up into rectangles, which we made thinner and thinner and thinner to get better and better approximations. Okay, just like that. For my multivariable case, when I have this rectangle, okay, and I got these boxes, if I make these boxes smaller and smaller and smaller, I get better and better approximations to my volume. Okay, so that's the idea. So again, I have this idea that I want to take that, you know, I have this approximation, my volume is approximately this Riemann sum over here, and I want to take a limit, and what do I want to make small? I want to make the area of the bases as small as possible. So I want to make this delta A as small as possible. So if we're going to take the limit as delta A goes to 0, and if we do take that limit, and if that limit exists, that should give us the exact volume, right? So when I take the limit, my volume should be exactly that right side, okay? So we see that we start to find the volume underneath the surface, the exact volume underneath the surface. We start with this approximation given by Riemann sums, and then we take the limit as the bases of our rectangle, the bases of our boxes get smaller and smaller and smaller. Okay. Now that's all well and good, and we kind of see, all right, maybe that's a feasible way to find the volume beneath the surface. But forget about volume for a second. This is a mathematical object in its own right. And what do I mean by that? Well, we could look at this type of sum and its limiting behavior and look at it for its own sake and not for the sake of calculating volumes, right? If we just kind of looked at these summations for a function, the limit exists whether, you know, if a limit exists, it exists whether we're thinking about it in terms of area or not. You know, we could think of this summation as kind of divorced from our real world interpretations of it, and just think of it for its own sake. Okay, so this mathematical object, this limit on the right hand side, is what we call the integral of f. And you might be asking yourself, well, you might be saying to yourself, well, we already have integrals of functions, right? So it doesn't really make sense to call this thing an integral as well, but it actually is. So integral, as we're in the multivariable class, we can start thinking of things in higher dimensions. Really, the integral doesn't matter what dimension we're working in. It's a very general concept. Whether we're working in 1 dimension or 2 dimensions or 3 dimensions, the formation of it is the same. We've seen a lot of parallels between the single variable case and the multivariable case already, and those parallels hold for higher dimensions. And if we kind of think about it in terms of the general concepts of like, okay, we have a function value times kind of like some sort of measure, whether it be volume or area, or excuse me, area or length of an interval. If we multiply our function value times our kind of measure, we get this Riemann sum, and then we can take the limit of the sum as the size of our measure goes to 0, and that, if that limit exists, we call it the integral. You know, it doesn't matter what dimension we're working in. Okay. Now, the limit of this thing is not always going to exist. Integrals aren't always defined they're not defined for all functions, right? So just like we saw with single variable functions, we'll need some conditions for integral to exist. We're not going to worry about it too much, but it should be stated that not all functions can be integrated. If a function is nice, meaning like, you know, that's not actual terminology, but let's say our function is continuous and bounded on a bounded interval, then yeah, the integral, this limit is going to exist. The integral is going to exist. Okay, so when that limit exists on our rectangular region D, we call that limit, we call it the integral of f on the region D. And we can give it a special notation if we had to write out this limit sign and these double summation signs every time. That'd be a bit cumbersome. So we just kind of compactify it all and denote it as this. Okay. So instead of having there's a couple ways to write this, but on our right side, we have our limit, right? And we're saying that, okay, if this limit exists, we're going to call it the integral. And instead of writing this every time, what we're going to do instead is use this slightly more compact notation, okay, here. All right, so what's going on with this notation? First of all, I have two integral symbols. And this is essentially telling us we're integrating over a 2-dimensional domain, the xy plane. Okay, and then what is this D here? Okay, instead of having like bounds, we can have, we'll see bounds later, but for right now, instead of trying to write bounds for my integral, I'm just going to write this D underneath it. That stands for my domain. Okay. And then what do I have inside? I have my function fxy. And then instead of having a dx or a dy or something like that, I have my dA. Okay. So this is very general and maybe vague notation, but that's what this right side, that it stands for, this right side. And we're going to see ways to make a bit more sense of this in just a little bit. Now, a note about terminology and notation. Okay, we said that this limit thing, we can call it the integral. We could also call it the double integral if we want to be kind of specific about what dimension we're working in. You know, we're working in, as I said, the 2-dimensional domain, the xy plane, and we have this double summation sign. So we can call it the double integral on D, where D is our domain. Okay, and we might denote it with that double integral sign, as I said. Now, it's also valid to just use one integral sign. It's in, you know, even if we're working in 2 dimensions, I might just write one integral sign. as I said, we can integrate in pretty much any finite number of dimensions. I could integrate in like where my domain is like 10 dimensional. So I wouldn't want to write 10 integral signs, right? So I can just write one, and then as long as, you know, we know that our domain is, as long as it's clear what the domain is, you know, this is not a problem. Okay. So if you're reading math texts in the future, whether you're, you know, doing your engineering or whatever, what have you, computer science, wherever you might be using calculus, you might see an integral, and it seems like it should be a multiple integral, multiple dimensions, but they just have one integral sign. Well, that it could still be a integral over higher dimensional space. Okay. And let's see, for our function r2 to r, we have our variables x and y in here. But again, if we're working in higher dimensions, like r5, I wouldn't want to write x1, x2, x3, x4, x5 in my function every time. So instead of writing those, I can just write a vector x. Okay. So all these things are essentially the same. Now, as I said, this limit doesn't always exist, right? The integral isn't always defined, but for functions with nice properties like continuity and boundedness, the limit will exist. And if the limit exists for our function f, we say that f is integrable on D. Okay, so if the limit exists for that Riemann sum, we call it the integral of f, and we say f is integrable on D, our domain. Yeah. Now, that's the theory of the integral for multivariable functions, and we kind of gave example, a kind of graphical example for functions r2 to r, but again, it works in higher dimensions as well with just minor modifications to our thinking. As I said, that's the theory. Speaking of theory, the next chunk that's covered is, let's see, in example 1, they talk about what estimating volume using Riemann sums, and we don't need to do that. That's just a hassle. Then it talks about the midpoint rule, again, as kind of an approximation to a volume. We don't need that. Okay. We want to actually get to the integration. So the next topic we're going to cover is iterated integrals. Okay. So we can think about the first chunk of this lecture as the theory behind the multivariable integral. Okay, the idea behind it, and the iterated integral is going to be the tool that allows us to calculate these things. You know, I've given you the theory for this multivariable integral, but I haven't actually shown you how to calculate it, have I? Okay. All right, and to do that, we need just one more theorem. Okay, that's going to make things so much easier, make our life so much easier. It is Fubini's theorem. So as I said, the previous theory doesn't tell us how to calculate it. To calculate these integrals, we're going to at least need to be aware of this theorem called Fubini's theorem. And Fubini's theorem, let's look at the statement first, and then I'll kind of give a disclaimer afterwards. Okay, so if f is continuous on the rectangle D, then its double integral, which is what we just discussed in theory, is going to be equal to this thing we call an iterated integral. Okay, so what is this iterated integral? I have a function of x and y, and notice the structure here. I have this integral sign from a to b. Okay, and notice my x is going from a to b. And then I have dx here. Okay, so I can think of this as one integral inside of another. Okay, so I have this this integral in terms of x nested inside an integral in terms of y. And how do I calculate this iterated integral? I just integrate this normally using my single variable tools, and I integrate it in terms of x. I basically treat x as my variable and y as a constant, similar to how I did partial derivatives. So I calculate that that integral, treating y as a constant, and that gives me some numbers and maybe like a function. And then I take that function and now I integrate it in terms of y. Okay. Now this, maybe it doesn't make too much sense right now. So let's go ahead and skip down and do an example real quick. And it should really elucidate everything. So let's consider this iterated integral. Okay. Now, the first thing I'll say before we begin is that the order of things matters. Okay. So when I have this iterated integral, always think of it with kind of like parentheses here. Okay. And then what do we integrate first? We start from the inside and work our way out. So what do we have? We have this integrals in terms of x. So I have dx here. So that tells me I need to integrate in terms of x. Okay. And then this integral sign here, okay, with these bounds corresponds to integrating in terms of x. And this integral sign corresponds to integrating in terms of y. Okay, we have to be very particular about our order. All right, so let's try this iterated integral. Okay, so as I said, how we do this is I kind of imagine parentheses there, and I integrate this just using my single variable tools. So at every step, I'm going to keep both integral signs. Okay, so I keep my 0, 4 there, and then I calculate my integral in terms of x on the inside. Okay, what is that integral in parentheses there? Well, again, I'm going to treat y like a constant. So forget about the y and look at x squared. What's the integral of x squared? It's x cubed over 3, right? And then it's times that y, which I'm thinking of as a constant. And it's a definite integral, so I would evaluate it at my bounds 1 to 2, right? All right, so it gives me that. And then, you know, I can think of parentheses there, but I don't have to write those parentheses. All right, and then let's continue simplifying this. Let's plug our bounds in to our indefinite integral there. So I get y times what? 2 cubed is 8 over 3 minus 1 over 3, right? All right, so I get this term, and then I simplify some more. Okay, so what am I left with? I'm left, you know, I got a constant, but really I integrated and I got a function out, right? I got 7/3 times y. That's still a function. It's a function of y, right? So now I have, I'm left with this integral. But again, this is just a single variable integral, and I know how to deal with that. 7/3 is obviously a constant. I could pull it out of my integral if I wanted. And then I have the integral of y dy. I know how to integrate that. Y squared over 2, evaluated from 4 to 0. let's see, 16 over 2 is 8 minus 0. Okay, so let's see, we get 56 over 3. All right, and that's our iterated integral. All right, let me plug this iPad in before I lose you guys. Okay. All right, so now that we've seen how to do the iterated integral, let's kind of scroll back up here. All right, so what Fubini's theorem is telling us is that that object we created, or that we defined, that integral on our rectangular region, can be calculated in this way. So essentially, Fubini's theorem allows us to take this thing that we didn't really know how to calculate and break it up into pieces, which we did know how to calculate. Okay, so we take our double integral and turn it into this iterated integral, where we do the inner integral first and then the outer integral. Okay. Now, my disclaimer about Fubini's theorem. You noticed I didn't justify Fubini's theorem. That is because Fubini's theorem is super hard. And you know, this is kind of a watered down version of Fubini's theorem. It's not something, it seems simple, right? It's kind of a simple statement and kind of fundamental, so you'd think it'd be nice and simple. It's you know, on the complex side of things. It's a little complicated. So it's kind of beyond the scope of this course to talk about why it works. But just take for granted that it does. All right. Now, in Fubini's theorem, what did we say? We said that that double integral, okay, is equivalent to integrating in terms of x and then in y, in terms of y. Okay, but we could have just as easily switched it. We could have done integrating in terms of y and then in terms of x. And so if we kind of combine those two ideas, we see that it doesn't really matter what order we integrate in. We should end up with the same result. Okay, and I invite you guys to kind of go back to this integral and switch our bounds around. Now, be careful, okay? Be careful about how you interpret what I'm saying. It's not okay to just switch the dx and dy, okay? Okay, I can't just integrate in terms of dy and use these bounds, okay? If I'm gonna switch my order of integration, if I'm gonna integrate in terms of y first, I also need to switch my bounds. Okay, so if I'm switching dx and dy, I also need to switch my bounds. Okay. But as long as I do it right, it's fine. Okay, so if I'd calculated this integral instead, this iterated integral, I should get the same thing. And I invite you guys to, we've calculated this one. I invite you guys to try this one and verify that you get the same numerical answer. This, yeah, I'm not going to say anything. I'm not going to try and confuse you guys. This works for everything you're ever going to see, most likely. So don't worry about it. But in later sections, okay, this is working out nicely. Because we have just nice simple constants in our bounds of integration. In later sections, we are going to see something slightly more complicated where we have to be careful about how we switch the order of integration. And that's usually going to be when there's like a variable in my bounds of integration. So let's say I'm integrating in terms of x, x first, but this upper bound is, it's not a constant, it's my variable y. Okay, and then, you know, we got to be a little bit careful when we're switching our bounds of integration, but we'll cover that topic when we get to it. I just want to give you a little preview that, okay, switching these bounds of integration is fine if we have just constants in our bounds of integration. If we don't have constants, we're going to have to be a little bit more careful. So as I said, Fubini's theorem is really big, and it allows us to split up these multivariable integrals into simple single variable pieces. And I can now at this point give another kind of naive, or again, not using naive as a insult or whatever to this way of thinking. But it's just not very rigorous, right? It's just kind of a loose idea. Okay, so let's say I want to find the volume underneath a surface. Okay, so on the one hand, we should have that volume is equal to that double integral. And let's assume I haven't learned Fubini's theorem yet. What's another way? What's a kind of a way to justify using something similar to Fubini's theorem? Okay. All right, so on the one hand, we know this volume is going to be equal to this double integral. On the other hand, consider, let's fix y. Fix y and consider the integral f of x, y in terms of dx. Okay, so what does this mean? Now at this point, I want to kind of copy and paste my, so I don't have to keep going all the way back up here. Okay, I'm going to copy and paste this thing. Let's clean it up a bit. It's the work of but a moment. Okay. So on the one hand, this double integral, this double integral would kind of represent that whole volume underneath that surface, right? On the other hand, let's fix a y value. So let's kind of pick this y value right here, and let's take a slice of this surface along that y value. Okay, so maybe my surface along that y value, maybe it's this green curve along the top. Okay. Okay, and I'd kind of take this slice, and then let's lay it flat out on the page. Let's say it looks like this. Okay. Now this slice, it's two-dimensional and it has an area. Okay, and you know, I kind of know what, I know how to describe the top of this slice. It's my function fxy, where y is constant and x is changing, right? Because why is that? Because I'm taking a slice through y, so my y is the same in this whole slice, and my x is changing. So this top is described by a multivariable function, but really it's kind of, when I hold y constant, it becomes a function of a single variable. And so I could talk about the area of this. What is the area of that? the area of this slice would be fxy, where I'm holding y constant, from a to b of dx. All right, so this gives me the area of my slice. And then kind of naively, I think, well, if I take slices everywhere and add up those areas, somehow they should kind of give me a volume, right? And that's essentially what's going on. But as I said, it's kind of a naive view. A little bit more, maybe a little bit more nuanced is, I say that this thing gives me the area of my slice. And then I'm kind of multiplying it by this term dy, which is kind of like we could think of as the width of each slice. So I have an area. I've kind of like this area of my slice, this surface area, and then I'm multiplying it by a width dy. So an area times a width is kind of like a volume. So this is kind of like giving me my volume of my slice, and then I'm integrating from C to D, meaning I'm kind of adding up all those volumes of all those slices to get my total volume. Okay, and essentially it's kind of a naive way of arriving at the Fubini's theorem, right? We're saying the volume should be equal to this double integral, and then we're saying on the other hand, well, we could kind of think of this volume in this way as well. So we should suspect that these two things are equivalent. So that's just one way you could think of it. Now, a disclaimer about integrals, these multivariable integrals in general. We've been talking a lot in terms of volume, and as I said, that's a good way to start thinking about these integrals. But just like with areas for the single variable case, it's kind of a limited view, right? For the single variable case, remember for the single variable case, okay, if I have a positive function, right, if f is always positive, then yeah, the integral gives me the area beneath the curve, okay? But what if f is negative? All right. Okay, so what if f is down here between a and b? Then the integral is going to give me a negative number. So does it make sense for area to be negative? And what about if f is, positive for a while and then negative? And maybe these this integral, maybe these pieces kind of cancel each other out, and I see my integral is 0. Okay, is the area of this thing somehow 0? So that it's kind of a limited understanding about it. Maybe one of the ways around it is we could think of the integral as something called like a signed area, meaning either positive or negative. So maybe we have like a positive area and a negative area, whatever that means, and they can cancel out to some extent, or maybe one outweighs the other. But that's one way to think about it. But really, we should just kind of, let's see, I guess you guys are all more practically minded than I am. I kind of tend to think of things in pure mathematical terms just because that's where my focus is, but maybe you guys who want to go off and be engineers and all that are more focused on the practical applications, so this doesn't really make sense. But my advice is, if you can, try and think of this in abstract mathematical terms, where the integrals are just the limits of Riemann sums, and then yeah, they have these applications like area and volume, but that's not their definition. That's not their primary nature, I suppose. Okay, so with that out of the way, let's continue. So that's just the explanation of my kind of naive view of these slices. Okay, average value, just a, this average value, we're getting to the end of the section now. There's a little bit on average value, and then I'm just going to work a couple integrals for the end of this video. Average value, the integral, this multivariable integral, the iterated integrals give us a nice way to calculate the average value of a function on the domain. Okay, so if I think again, if I kind of go back up to my my curve here. My function, my multivariable function, is taking a lot of different values on this surface, right? It's kind of higher up here, and then maybe in this corner it's kind of lower. What's the average value? How could I find the average value of my function on this area? Okay, it's not as simple as just adding up some values and then dividing by the number of values, because there's an infinite number of points, right? So for all these points down here, they're mapped up to, this surface. There's an infinite number of points to consider. So how can I find the average value of my function? Well, what I do is I integrate my function, okay? And think of this as like, think of the integral as giving you like the total value of f. Like adding, kind of, it's not really adding up f at all the points, but maybe kind of like a mass. You have this point associated with this value, and if you kind of think, okay, it's kind of like a weighted sum of these f values. So if you have a large area of your domain has kind of all the same f values, okay, then your integral is probably going to be pretty close to, let's say all these points in this region here have the value c, okay, and then this base has area a, okay. The integral on that region is roughly c times a, okay, and the larger this the larger the number of points with the value c, the closer your integral is going to be to just like c times the area of the region D. Okay, so you can kind of think of it as a weighted sum of our functional values. That may or may not make any sense to you, but the short story is, if I integrate my function, I can think of that as kind of giving a sort of like sum of all the values in my domain. And then what I do is I divide by the area of my domain. That's what this A parentheses D means. It's the area of my domain. And so that kind of gives the, it doesn't kind of give, it gives the average value of f on my region D. So essentially what I have is 1 over area times the total value of f equals the average value of f. Okay. I'm not going to give an example of this problem. I'll look at the WebAssign homework, and if there's a problem on this topic of average value, I'll cover it in the lecture. I just wanted to give a couple more examples of this iterated integral and this these double integrals for our rectangular region. So let's just do a couple quick integrals. All right, so starting with this one. So again, let's be careful how we look at this. Okay, let's spread these out just a little bit. Okay, what do I integrate in terms of first? Well, imagine your parentheses. Okay, what's the integral? It's in terms of y. This dy tells me I need to integrate in terms of y first. Okay, and I could switch these if I wanted, but you know, I don't see any reason. Sometimes it's easier if you kind of switch the order of things, but I don't see any reason to at this point. So let's just go ahead and integrate in terms of y. Okay, so let's treat our x's like constants and integrate in terms of y. Okay, so what's the integral of 6x squared y? Well, that would be 6x squared y squared over 2. And then what's the integral of minus 2x? That'd be minus 2xy. And then I need to evaluate from 2 to 0, right? And then I'm keeping my integral, my dx, and I'm keeping my integral sign out front. Okay. Next step is to plug in your bounds. Go ahead and plug in your bounds and simplify. So for 1, okay, I plug in 2 and I get what? 6x squared. I'm not plugging 2 in for x, I'm just plugging it in for y. Okay, I integrated in terms of y and now I evaluate for my y's. I plug 2 in for y and I get, okay, y squared would be 4 over 2 minus 2x times 2 minus 4, 4x. Okay, so that's what I get when I plug in 2. And now I subtract away what I get when I plug in 0. What do I get when I plug in 0? Well, I just get 0. Okay, let's go ahead and simplify again. So I get 4, 1. Let's see, 6 times 4 over 2, 12x squared, right? Yep, 12x squared minus 4x dx. Okay, so now I'm just left with this function in terms of x. I've eliminated all my y's, and now I just have this function in terms of x, and now I just need to integrate in terms of x, and I don't see any problem here. Now we're just kind of reduced to our single variable case. So I just continue integrating normally. What's the integral of 12x squared? That'd be what? 4x cubed. What's the integral of minus 4x? That'd be what? Negative 2x squared. Evaluated from 4 to 1. I plug in my 4. Let's see, I get 4 times what? 4 cubed is 64 minus 2 times 16. Okay, minus 4 times 1 minus 2. Okay. So it's 64 times 4, 256. 256 minus 32 is what? 224, something like that. Minus 2, something like 222. Double check my math on that. All right, so 1 integral down. Let's do 2 others. Okay. So let's integrate xy squared over x squared plus 1. And we're seeing a couple different ways to present our integral. Okay, so notice that in this problem, okay, this is what we were given, right? We were given this, and they gave us the bounds. They kind of wrote the 2 integral signs, and then they put our bounds on each one. Here's another way to present our integral, and it seems a little more vague, right? And this is maybe a little test of your understanding of Fubini's theorem. Okay, so instead of giving you the iterated integral with our bounds, you know, 0 to 1, negative 3 to 3, they just tell you, okay, do the double integral over this region, and then they tell you what the region is. They say, well, the region is 0 to 1. What is 0, 1, x, negative 3 to 3? I would kind of pronounce this 0, 1 cross negative 3, 3. Okay, what is this? Let's kind of draw the region real quick in the, well, let's just draw it in the XY plane. Okay, X, Y. What is this region? Okay, this is my X region, or this is my X interval, this is my Y interval. So my X is between 0 and 1, and then my Y is between, let's see, -3 and 3. So my rectangular region is this. Okay. All right. Does this help us? You know, that's just drawing the region. But how do I write the bounds? You know, I don't really need to draw regions for all my integrals. How do I write the bounds from this thing? Well, what's important to know is that this is your X region, this is your X interval, this is your Y interval. So I should, when I integrate, okay, when I integrate in terms of X, it should be from 0 to 1. When I integrate in terms of Y, it should be from -3 to 3. So I could write it like this, and now I need to make sure I get my dx and dy in the right order. Okay, so if I write my integral bounds like this, I can set this up before I even put my function in. Okay, so I set up my integral signs in my dx dy, and I make sure I got them in the right order. That this 1, 0 goes to my dx, this -3, 3 goes to my dy. Okay, and then I can throw my function in there. xy over x squared plus 1. Remember, Fubini's theorem tells us that this is the same thing as this iterated integral. Okay, and then this iterated integral we can actually solve, right? So let's go ahead and solve this. All right, and then these two problems are kind of good examples that we still have all our tools from the single variable integration theory. Okay, so let's see, xy over x squared plus 1. We're integrating in terms of x first. Okay, so I'm looking at this integral, and I'm treating y like a constant. And if it helps, what you can do when you have a y, notice that this y I can factor out, right? I could rewrite this stuff inside my integral like this. Okay. Now, if y if I'm treating y like a constant, then just like with any other integral, I can just pull it out of my integral sign, right? Like if it was the number 4, or well, it actually looks like the number 4. So let's say I have a y here. Let's say if y was just the number 5, I could pull that number 5 out. I know I can pull it outside my integral, right? Well, if I'm treating y like a constant, I can do the same thing with the y. I'm going to pull it out front. Okay, and now it's maybe a bit more clear how to proceed with this integral in terms of x. Okay, so just use your single variable theory. Okay, how could we deal with this? We could do a u substitution. U equals, how about x squared? There's a couple u substitutions you can make there, and then du would be what, 2x, and so du over 2x equals dx, excuse me, du equals 2x dx. Okay, and then you work your u substitution. Your inner integral becomes what, 1/2 1 over 1 plus u du. Okay. Now remember, u substitution changes your bounds, and so you should recalculate them, but I'm going to leave that blank for the moment. Okay, and then we have our y out front. Okay, and so my integral after a u substitution becomes this. All right, now this du integral I can solve easily. It's 1/2 ln absolute value of 1 plus u. Okay, and then I need to evaluate that at my bounds. I have my y out front. Okay. Now, instead of evaluating at the new bounds, what I can do is undo my substitution and use my original bounds. What was, oh, and this isn't y, that's just u, right? Okay, so ln of 1 plus u, u is our u is x squared. And I'm evaluating from what? 1 to 0. Okay. So I evaluate that, that stuff inside my parentheses. What does it evaluate as? Let's see, 1/2 ln of 2 minus 1/2 ln of 1, which is 0. So it should just be 1/2 ln of 2 dy. Okay, and then again, I have a simple integral. Now this 1/2 ln of 2 looks complicated, but it's just a constant, right? Ln of 2 is a constant, 1/2 is a constant. So I can pull those outside my integral. And then what's left inside my integral, it's just the integral of y from -3 to 3. I can evaluate that. Y squared over 2 from 3, or -3 to 3. And then I evaluate that term in parentheses. And what is that? Let's say 3 cubed is, or excuse me, 3 squared is 9, 9 over 2. Minus 9 over 2, 0. So it looks like my integral goes to 0. Hopefully I haven't made any mistake on there. It's possible, but hope not. And then let's look at this final example, x over 1 plus xy. And again, we have a slightly different notation here. So in this example, they said, okay, R is this region where they gave us one interval across another. Okay, so that's one way to present our information. Another way is to use this set notation. So I'm told to integrate on R, and then they tell me R is equal to this, and they're using this set notation. So this is, what is this saying? It says x is between, this set notation is saying, okay, our domain is all the points x, y, where x is between 0 and 1, and y is in between 0 and 1. So let's draw that, you know, if this is my xy plane, what is that region? Well, it's just 0 to 1 cross 0 to 1. It's just that square there. Okay, so how could I write this as bounds of an integral? Well, my x, let's do our dx. Our x is going from 0 to 1, and then our y is going from 0 to 1. And then let's just plug our function back in. Okay. Integrating, let me think, how did I integrate this? I tried this one before. I believe I did a u substitution. Let's try a u substitution. How about u equals xy, du equals y dx? No. We could do this one if I integrate in terms of y first. So let's switch our bounds, and this would be an example of how maybe switching bounds can help. So if I want to change my order of integration, okay, let's say I want to integrate in terms of y first. I can do dy and dx, but then I got to switch the bounds, right? But the bounds are the same in both cases, so I switch 0 to 1 and 0 to 1, and I end up with the same thing. Okay, so now I'm integrating in terms of y first, and now let's try u substitution. How about u equals xy, du equals x dy, so du over x equals dy. I might be on the wrong track with this. So that integral becomes 1 over 1 plus, no, maybe that works. 1 over 1 plus u du dx. Okay, and that messes those bounds up. So this is ln of 1 plus u from blah, 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 0 dx. I undo my substitution. One plus xy from what? 1 to 0. Then I plug in my bounds and I get ln of 1 plus x minus ln of 1 plus 0, which is 0. So I just get this. And then let's see, on the interval 0 to 1, I can drop the absolute value bars because this is always positive. Okay, so I just have ln of 1 plus x. And could I integrate this using integration by parts? How about integration by parts? So let's pretend there's a 1 there. Okay, and that 1 is a dv, and this is a u. My integral will be equal to what? X ln 1 plus x from 1 to 0 minus the integral from 0 to 1 of x over 1 plus x dx. Yeah, that's fine. Where is it? Oh, yeah, and then we could do another u substitution here. Let's call it a v substitution. This is x ln 1 plus x from 1 to 0. And then we could rewrite this as well, v minus 1 over v dv, which is the integral of 1 minus 1 over v getting sloppy here towards the end. It's the last problem. I'm trying to go fast. I undo my substitution. There's probably an easier way to do this, but this is how let's see, what did I there's got to be an easier way to do this. Okay. So let's see. Now we have our integral, our indefinite integral, and we can evaluate our bounds. Let's see. I plug in 1, I get 1 times ln of 2. I plug in 0, I get 0 for this. Okay, so this first term is just ln of 2. Okay. What about this integral here? Let's see, I plug in 1 and I get 1 plus 1. So I get 2 minus ln of 2. Okay. And then I subtract what? 1 minus ln of 1, which is 0. Okay. So I get ln of 2 minus 2 plus ln of 2 plus 1. So it looks like I get 2 ln of 2 minus 1. Again, I wouldn't be surprised if I made a mistake somewhere. So this one was fairly complicated. Don't freak out too much. They're probably not all going to be this complicated on your homework. And see if you guys can find a simpler way to do this and check my work. All right, that's it for this video. More to come.